Hello everyone. I hope you have been enjoying this course. I hope you find it useful. If you have any questions, please post in the comments, or you can also feel free to email me if you have any questions. Okay. Right. Okay. So in this lesson, this is a new lesson. In this lesson we are going to study Stokes equations in 2 dimensions. Okay, so this is one step before we actually solve full Navier-Stokes equations. The transition from Stokes to Navier-Stokes is very straightforward. The only difference between the Stokes and Navier-Stokes is that in Navier-Stokes we have an extra term for convection. Okay, so and by solving Stokes equations, we learn a lot of things that are equally applicable for Navier-Stokes. And Stokes equation is a linear equation, so it makes things little bit of easier to understand, okay, and also code, also like to implement, okay. Now, okay, so as usual, we start with our governing equations, okay. So when we talk about study Stokes equations, we have the two main governing equations. One is the momentum equation, and the second one is the incompressibility constraint on the velocity. Okay, the divergence of velocity is 0. Okay, so here mu is the viscosity. Okay, and u is our velocity variable, p is pressure, and f is the body force. Okay, so here notice the difference in the letters. Okay, so p is this p is just the letter. Okay, no highlight. Okay, no boldface. Whereas u and f are in boldface to show that they are vectors. Okay, so this is how we distinguish between scalars and vectors. Okay, so boldface variable is a vector, or it could be it could be a tensor to represent higher order variables. Okay, whereas p is a scalar and mu is also a scalar. Okay, and here this is nabla. This is a gradient operator. Okay, and this is delta. So this is a Laplace operator. So delta u is del nabla dot nabla u. Okay, so this is the divergence of gradient. Divergence of gradient of u. This is the Laplace operator. So here we have second derivatives. Okay, and in the second equation we have divergence of u nabla dot u equal to 0. Okay, so these equations are typically supplemented with the boundary conditions. So we have typical Dirichlet boundary conditions where on part of the boundary the value of the velocity is specified, or on a part of the boundary we have traction specified. So this traction is the stress tensor and the normal. Okay, so the dot product of the stress tensor and the normal. Okay. So here sigma is the stress tensor, and in this case it is a pseudo stress tensor because we already removed one part of the strain. Okay, the strain tensor. Okay, strain rate tensor. Okay, we have already removed one part of the strain rate tensor by making use of the fact that the flow is incompressible. Okay, so we have only one term here, which is the Laplacian operator. So because of this, our stress tensor slightly changes, and we have like this. Okay, so our stress, this is called pseudo stress tensor, and its expression is mu nabla u, and again here nabla u the gradient of u, and minus p I is the identity tensor. Okay, so in 3 dimensions, our gradient of U is a 3 by 3 matrix. Okay, so in 3 dimensions, it is a 3 by 3 matrix. So delta U is a tensor actually. Okay, so in 3 dimensions, it is a 3 by 3 matrix, and we write it in this fashion. Okay, so dou ux by dou x, dou ux by dou y, and so on. Okay, in 3D, we also have z component and derivative with respect to z. Okay, when we simplify to 2D, we have only ux and uy, and so we have only 2 by 2 matrix. Okay, so appropriately, we take the identity tensor as a 2 by 2 matrix or 3 by 3 matrix depending on the dimension. Okay, so these are our grounding equations. Okay, once we know that the PDEs, we can start deriving the weak form. Okay, so we follow our standard procedure. Okay, so we start with the weighted residual statement. Okay, so this is our residual. This is our residual of the momentum equation. So here I'm using the fact that delta u equal to nabla dot nabla u. Okay, so instead of delta u, I'm using nabla dot nabla u. Okay, so this is the residual of the momentum equation, and because this is a vector equation, that is, we have two components for f in the 2 dimensions. So we have two equations. Okay, this is a vector equation, not a scalar equation. That is why we have the dot product. Okay, this is not a scalar product anymore because it is a vector equation. Our test function w is also a vector. Okay, so again has two components, wx and wy. So since both are vectors, to get a scalar, we take the dot product. Okay, and in the case of the divergence, zero divergence, the second equation, the incompressibility constraint. So here the divergence of u is a scalar. So here we have a scalar product with the test function for pressure. Here w is the test function for velocity u and q is the test function for pressure p. Okay, so again, noticing the differences in the bold, like in the font type. Okay, so w is boldface, that means it is a vector, and q is not. Q is a scalar. Okay, so in this case, since we have two independent variables, we need two separate test functions, w and q. Okay, once we have the weighted residual form statement, we apply we split the integrals. Okay, and then we apply the Gauss divergence theorem. Okay, so once you do all the steps, okay, so here, so I have done all the steps. So I'm leaving this as an exercise so that you understand like how this works in practice. Okay, so what we do, we transfer one derivative from this term to w, so it becomes nabla w, and we have one nabla u, nabla here, okay, nabla u. Okay, this is gradient of u, and we get gradient of w. Since both of them are tensors, we need a contraction operator. Okay, this is like a dot product but for tensors. Okay, this is using the integration by parts, and then using the divergence theorem, we get the boundary term for the traction. Okay, for the Neumann boundary condition. Okay, and then this w dot f, it goes to the right hand side because we know f. And for del p, sorry, this nabla p, okay, again we transfer this derivative to w. Okay, it becomes nabla dot w, that is divergence of w multiplied by p. And because of the change of variable, uh, sorry, since we are transferring the derivative here, the signs get reversed. Okay, so here we have minus, it becomes plus, and here we have plus, it becomes minus. Okay, and for the second one, we don't change anything, it remains as it is. Okay, so this is our weight form using the tensorial notations. Okay, so here gradient of u, gradient of w are tensor, so we have the tensor contraction operator. Okay, this is the okay, so that means, so we multiply the terms component wise and add them together to get the scalar. Okay, so if you take like u11, okay, if you take this gradient of w as a and gradient of u as b, then the transaction operator is like this. Okay, so a11 b11 plus a12 b12 plus a21 b21 plus a22 b22. Okay, we multiply component wise and add them together. Okay, and for the sake of deriving the finite elements like matrices, it is difficult to work it is difficult to work with these tensorial notations. Okay, when we derive the finite element matrices. So what we do, we rearrange this in the vectorial form, in the vector form. Okay, so that means, so although the notations are same, when we write in a vector form, so we replace this, okay, this transaction operator use like by taking del u, this gradient of u and gradient of w as vectors. Okay, so here, so I am taking this gradient of u in this fashion. Okay, so the reason is, if we take in this fashion, then gradient of w is also in this fashion. So we transpose gradient of w, that becomes 1 by 4 matrix. So 1 by 4, 4 by 1, 4 by 1, we get 1 by 1, which is a scalar. Okay, so when we multiply this, we get a scalar. And by writing it in this fashion, when we discretize using basis functions, we can easily get the matrices in a straightforward manner. Okay, as you note here, okay, we replace the dot product with the vectorial form, so that's why we have the transposes. Okay, note here, all the boldface letters are vectors. That is why we need the transposes when we go to like matrix vector form. We don't change anything here because this is the divergence. Okay, divergence of w and divergence of u, and it is a scalar product. Okay, so that is why there is no change in these terms. Okay, so now we have the weak form and we have it in the vector form in the matrix vector notation. So our next step is to discretize it. That is, we approximate solution for u and p. Okay, so now here, since u is a vector, like, and it has two components, we like here things become more complicated when compared with the 1D problems where we have only one variable. So what we do here is, so we take the same basis functions for both the components, like for x and y degrees of freedom, we take the same basis functions, but since you have 2 degrees of freedom, okay, if you call it like that, okay, so 2 degrees of freedom, ux and uy, so what we get is a 2 by 2m matrix. So if we assume that there are m basis functions per element, so this is our basis function matrix. Okay, so nu, and this is our the dy of vector u. Okay, and similarly the test function w. Since we are using the Delartin method, we use the same basis functions for the field variable and the test function. Our field or solution variable u and our test function w. Okay, so once we know u, we can calculate its gradient. Okay, its gradient. Remember, so we are using the matrix vector form. So we have this 4 by 1 matrix for the gradient of u, and by using this basis function, this approximation, we can calculate the derivatives of x and uy with respect to x and y, and then prepare our matrix vector notation in terms of the gradients of the basis function and the dy of vector. Okay, and this is our gradient matrix. Okay, gradient matrix for u. Okay, and similarly for w, we get a gradient of w, and our gradient matrix is the same. Okay, try to derive it on your own. So you see. Okay, so you can see how we come up with these expressions. Okay, now this is gradient of u. We also need the divergence of u. Okay, so divergence of u is dou u by dou x, so dou x by dou x plus dou u by dou y, and this is a scalar. We get a matrix of 1 by 2m. Okay, with a for an element with m basis functions, so 1 by 2m. So we denote this as a divergence matrix. Okay, so du. Similarly, for the divergence of w, that is function, we have du w. Okay, it looks complicated, but once you derive it on your own, it will start with ux. Take ux. Okay, ux will be nu1 multiplied by u1x plus nu2 multiplied by u2x plus nu3 multiplied by u3x and so on plus num multiplied by umx. Okay, and similarly for uy, and then calculate the derivatives, and then you can see why we get this matrix. Now we have described u. Similarly, we approximate the other variable p. Okay, so p is a scalar. Okay, so that is why this expression looks very similar to what we use in the case of 2D diffusion equation. Okay, so now we assume that there are n basis functions for variable p, and this is our dy vector for pressure p. Okay, and similarly for the test function q, we have npq. Okay, so with these approximations, and we can take the expressions for u equal to nu, and for w, p, q, and the gradients. Okay, and we substitute them in our weak form. Okay, so this is our weak form in the vector form, in the matrix vector form. So using FE approximation. Okay, so what we do for gradient of w, we have guw. For gradient of u, we have guu. And for gradient of divergence of w, we have duw. Okay. So again, in order to recover the scalars, we need to use the transposes. Okay, for w, we have nuw transpose. Okay, so you need to be careful here. Okay, so here, like even here, we don't have the vector. Both are scalars, so it is scalar product. So it is fine here. But as long as we have the discretization, so we get vectors and matrices. So in order to be consistent with the dimensions, that is the matrix dimensions, we need to use the transposes. Okay, be careful here. And for the second one, okay, in here. Okay, so we need to use the transfer q. We have npq. Okay, so we use transpose here, and for divergence of u, we have du. Okay, so next, what we do for arbitrary w and q, again, like we separate the terms. Okay, so we apply the transpose. Okay, matrix transpose. Okay, that this becomes w transpose gu transpose. and then we take the W transpose outside and separate the terms. Okay, so W transpose outside. So we get this mu GU transpose GU and then multiplied by U. Okay, and du transpose NP. Okay, we have minus here multiplied by P. Okay, so for arbitrary W. And then on the right hand side, we get this expression. Okay, and for the second one, we take for arbitrary Q. So we get Q transpose outside. Then in the integral, we will have NP transpose du. Okay, and then multiplied by U. Now, as you can see, I have like separate brackets for each terms. Okay, so so if we write them, these two equations in the matrix form, the black matrices, so we get 2 by 2 matrix. Okay, so this. Okay, so this first expression this in the brackets here. So this is our KUU matrix. Okay, so okay, so KUU multiplied by U, and this is our KUP matrix. Okay, KUP matrix. So KUP multiplied by P. So we will move the minus into KUP equal to FU, and this entire thing inside the bracket is FU. And in the second row, we have this term. Okay, so this is our KPU, KPU, KPU. And we don't have PP term. Okay, so it is 0. And you might notice KPU and KUP, they are transposes, but with multiplied by a minus sign. Okay, so KUP is minus of KPU transpose. Okay, now I would highly recommend you do the derivations on your own. Okay, right? Okay, so this is our 2 by 2 black matrix system. Okay, so we have to like when we implement it and solve it using an example later. Okay, so let me clear this. Okay, so this is our discrete system of equation. This is a 2 by 2 black matrix system. So in U, we have all the degrees of freedom corresponding to the velocity. In P, we have all the degrees of freedom corresponding to pressure. Okay, so here, this is our FU, the force vector, and these are our stiffness matrices. Okay, individual plots, KUU, KUP, KPU. Okay, so here, so we have two independent variables, U and P. U is velocity, P is pressure. Now, our big question now is, can we choose the elements arbitrarily? Okay, so now we have been implementing so far for 4-noded element, but we do know that there are a variety of elements available, right? So we have P1 element, that is 3-noded triangle, P2 element, 6-noded triangle, P3 element, 10-noded triangle. And for quadrilateral, we have Q1 element, that is 4-noded quad, which we have been using, which we have implemented. And we also have Q2 element, that is 9-noded quadrilateral, and Q3 element, 16-node quadrilateral. Okay, we have a variety of elements. Okay, so now the big question is, can we choose the same element for U and P? Let us say, okay, so we stick with our Q1 element. Can we use the same discretization, that is, okay, for both U and P? Let us say we can use and see if it works or not. Okay, so we are going to implement this matrix system, this system. Okay, these matrices, we are going to generate these matrices for each element and do the assembly and so on and so on using this example of lid-driven cavity. So this is one of the standard benchmark examples that we use to test our implementation. So this is a simple example here. So we have a domain of size 1 by 1. Okay, so it is a square of side 1. On the left side, on the bottom side, on the right side, it is a wall that is 0 velocity. Now on the top, we have a lid. Okay, so it's like we have a container and then you place lid, and then if you take the lid, if you slide the lid, then you see circulation, right? So this is what we do. So on the lid, we prescribe a horizontal velocity. Okay, so horizontal velocity like x component of velocity with y component 0. Okay, so we prescribe the horizontal velocity with this profile. Okay, so typically it should all be 1. Okay, but if you impose 1, then it leads to some numerical issues. So what we usually use is this expression to smoothen out the profile at the corners. Okay, so this, as we increase a, we do approach in the limit, we do approach 1 everywhere, but to smoothen up the profile at the corners, the top right and left corners, okay, right and left corners, we use a. For a large enough value of a, we get like we approximate it well. Okay, now, okay, in the next lesson we are going to implement the code for solving Stokes problem for this example. Okay, again, so I highly recommend you derive the equations on your own. Okay, so that's when you can understand the equations and how these equations. I'm going to share the files on Google Drive so that you can access them and go through them at your own convenience.